163 kilograms, right? Acceleration is 4.20 meter per second squared, and net force is mass times acceleration. You're looking for net force. Straightforward question, 63 times 4.20. You should have got 265 newtons when you look at the significant figures. Okay, on question 2, see, just for the sake of putting this up there, it's going to come up in. Weight on the moon. Weight is mass times acceleration due to gravity. So mass is weight divided by acceleration due to gravity, which is 250 divided by 1.67 meter per second squared, and you get 150 kilograms. And therefore, the weight on the Earth would be, again, mass times acceleration due to gravity on the Earth, which, as you know, is 9.8. Therefore, the weight is 1470 newtons. When you look at the significant figures, it's 1.5 times 10 to the 3. Remember that mass never changes, but you already see that the weight changed. Didn't you notice that? The weight was only 250 newtons on the moon. But on the Earth, it's almost 1500 newtons. Please give me all your attention. We're reading this together, and it'll do you good on the exam. Suppose two children push horizontally. That word is really important. I don't know whether you noticed. Horizontally. That's important. But in exactly opposite directions. On a third child. Oh, so that means the third child is caught in between the other two and is in a wagon, right? The first child exerts a force of 75.0. Second, 90. Friction is 12. And the mass of the third child plus the wagon is 23 kilograms. What is the system of interest if the acceleration of the child in the wagon is to be calculated? The answer is in the question. What is the system of interest if what is to be calculated? The acceleration of the child in the wagon. So the third child is the system of interest, because that's what you're asked to calculate, correct? So when you draw a diagram, if I have done it, it'll look something like this. You have all the three forces now shown, and let me bring that mass up, all right. So that's very clear. 75 newtons applied by the first child, 90 by the second. Mass of the third child is 23 kilograms. In fact, that's the total mass, isn't it? Friction. Be with me and understand before you draw it and write and all that. Friction is always opposite to the motion. Now that's 75, that's 90. What direction do you think this will move in? To the left or to the right? What direction do you think the wagon will move in? To the right or to the left? Come on now. See how many answers I get? Come on now. To the left. Because it's 90, it's 75, isn't it? Yeah. Therefore, it'll go to the left. And if it's tending to go to the left, friction must be to the right. Because friction is always opposite to the direction in which the object is trying to move. Is that clear? Yeah. Okay. That's why friction is towards the right in this case. There's a lot of understanding that goes in there. Now let me explain this. Does anybody know what this force is? Maybe you do. Gravity. Weight. The weight. It's because of gravity, correct. And how much would that be?
23 times 9.8.
Very good. 23 times 9.8. And wait a minute. What is that force?
Natural force.
It's not called the normal force. Yeah, when you have an object kept on a table, the table is going to push back on the object, right? So that is all the forces shown now. The system of interest is the third child. It's like I have a lot of time here. Because part A says, what is the system of interest? Isn't that part A? That's why I wrote that. And the net force, all right, we only take the forces along the x-axis. We don't mix them up. Remember that. So if you're looking at the x, you only look at the forces along the x-axis. How many forces do we have along the x-axis? 1, 2, 3. That's all. And 90 is the biggest force. So 90 minus 75 minus 12. That's clear, isn't it? 90 minus 75 minus 12, so the net force is 3.00 newtons. Acceleration is net force divided by mass. So mass is 23.0, therefore the acceleration is 0.130 meter per second squared. Yes, Anna?
Doesn't the friction work both ways?
Nope. Friction is always opposite to the motion. You cannot have a force work both ways.
Oh.
If the object tries to go to the
At the same time.
To the left, then it's to the right, okay?
Yes.
All right, so that is very clear. Now, to do the D part, all you got to do is in place of 12, you got to have what? 15. And if you plug it in, you are going to get the answer. Okay, the friction is 15. I think your textbook uses a small f to represent friction. That's why I've changed to that. Then net force is 0. Oh, really? Why? Why? Because it is 0, correct? So that's right. Because if you take 75 and 15 and add them, you get 90. 90 minus 90 is 0, so there is no acceleration. Simple. All right. Well, in this question, the player is brave, but he doesn't have enough strength. So he's being pushed backwards by an opposing player who is exerting a force of 800 Newton on him. Is this the net force?
No.
Is this the net force, guys? Come on.
No.
No, that's just the force applied by one person, isn't it? Don't you think that the losing player is also applying a force?
Yes.
He's not just standing there like, oh, go, push me. No. So the mass of the losing player plus the equipment is 90 kilograms, and he is accelerating. The losing player is accelerating at 1.20 meter per second squared backward. Let me ask you this. What's the system of interest here? Is it the losing player or the winning player? Which is the system of interest? The losing player. Now it says, what is the force of friction between the losing player's feet and the grass? There, I couldn't have got a better diagram than that, you agree, okay? 800, force of friction is always opposite, isn't it? Think about this. The other player, this is the losing player, of course. This is the losing player. The other player is applying 800 newtons on him. On him. That's the system of interest. That's the losing player. And between his feet and the grass, force of friction is opposite to the force being applied on him. Make sense? Okay. Therefore, the net force is mass times acceleration, his. And in this case, we know the net force is 800 minus F, and acceleration is net force divided by mass. Therefore, when you plug it into that equation, 1.20 is 800 minus F by his mass, 90. Therefore, rearrange that, cross multiply. Are you getting that? When you multiply those two numbers, you get 108, and then switch sides and you get 800 minus 108, which is 692 newtons. Yes. And it says B is on the other side. Yeah. And letting you do it. So here I go. The B part, net force is again the force applied minus friction, you know that, and that is equal to mass times acceleration, isn't it? We've done that many times. 692. Where did I get that from? Isn't that the friction? We calculated that. Plus, what's the mass of this player? 110. Plus 90. Where did I get that from? Don't simply write numbers, please. It's of no use. Tell me, how do I get this? Hey, what's really happening? What's this winning player doing? Is he only pushing that other guy, or is he also moving? So you got to add their masses. Because this guy is actually moving the other guy and moving along, right? So that's why the two masses have been added. But both of them are moving at the same acceleration, of course. They are connected, they're moving together. Okay. That's why the masses have been added, and that gives you 932 newtons. And I tried to make a diagram. Don't laugh at my stick figures, please. I think he's pushing on his head. That's too bad. If it's football, that's illegal. Anyway, 800, 692. That was the first case. Second case, 932. Still the friction is 692. That, I hope, gives you a better idea. I don't know. Also, look, this guy, if he's not climbing, and if he's just hanging there, can you tell me what his weight is? What is his weight? 588 newtons. 60 times 9.8, right? Okay, he's not moving. Imagine he's not moving, just hanging there. Can you tell me what the tension in the rope is?
His weight.
Correct. His weight. He's not doing anything. So now we're looking at the forces along the y-axis, right? If both are not moving, the rope is not moving, he's not moving, we're looking at the forces on him. He's the system of interest. Are you listening to me? One force acting on him is the weight acting down. And if that was the only force, he would have gone down. So if he's not moving, then there must be an equal and opposite force acting on him, which is the tension in the rope. Did you understand? How many understood? Let me see hands. Oh, thanks. Now he is moving. In this question, he is moving. But how is he moving? Up. Good. How is he moving? Constant speed. So what is his acceleration? What is the acceleration of an object that moves at a constant speed?
That would be zero.
Zero, correct. Wait, no buts. Get the buts out of the way. Okay.
But it's subjective.
No, wait. He is moving at constant speed, right? So his acceleration is zero. So what's the net force? Thanks. Net force is mass times acceleration. Are you with me? If the acceleration is zero, what's the net force? Zero. Right, good. So in this particular case, even if he's moving, still the net force is zero. That means the tension is again 588 newtons. Makes no difference. I hope you heard me. So whether he's at rest, hanging there, or moving up or down at constant speed, the tension doesn't change. All right, let's look at the diagram. That's the guy. Those are the two forces. One, mg acting down, tension T acting up. All right, net force is mass times acceleration. In this case, the net force is T minus mg, isn't it? Yeah. I just took T to be positive. You can do it either way. So T is equal to mg. Therefore, it is 60 times 9.8, which is 588 newtons. That's the tension. Okay, look quiet. What is the tension? In this case, the same formula. Always, its net force is T minus mg is equal to m times a. Didn't we use that before? But what's the difference? In this case, what's the difference? Is the acceleration zero this time? No. In place of acceleration being zero, last time, this time you're going to have, how much is that? 1.50. That's all. Such an easy thing. So when you take it to the other side, you know negative mg is going to become plus mg, right?
Yep.
Okay. So you get 678 newtons. While you're writing this, let me ask you this. What if this guy was going down with the same acceleration? Remember, in this case, it's going up, right? Christian, let me finish the question. My question was, would the tension in the string increase or decrease? Just common sense, logic. If it's trying to go down, he's agreeing with gravitational force, isn't it? He's saying, yeah, you want me to come down, gravity? I'm with you. So will that reduce the tension in the string or increase it? Reduce. Common sense. When he tries to go up, he's fighting gravity. Oh, the string has to take it now. So how will that change if he was going down? Let's say for the exam I ask you, he's going down. How will this change? Instead of saying T minus mg, you would say T plus mg. Or in this case, it will become G minus A. G minus A. Let's talk about, what's that? The British call it a lift. What do you call it here? An elevator? Oh, you don't know what that is? Okay. If you are, you have those bathroom scales, the weighing scales, and let's say you have one of those scales, and you're standing on it, and it's not moving. The elevator is not moving. It'll read your correct weight, right? But what about if it's going up? Will it read your correct weight, or will it read more, or will it read less? I'm asking you. It's going up. Come on. It'll read more. But if it's going down, it'll read there. You got it. It's the same thing as this. So I can ask you a question on that. Good. Put it on record. All right. So if the elevator cable breaks while you are inside, and you are still on that weighing scale, what will that read? As you're going down, what will it read? What will the bathroom scale read? Come on. It will read 0, right? Why? Is it going down or up now? Down. So is this going to be plus or minus? Minus. Minus what? What's the acceleration with which it's going down? 9.8. So 9.8 minus 9.8, according to me, is 0. Therefore, it'll read 0. Oh, so you became weightless, correct?
That's why it's fun to jump on an elevator.
Exactly. It is. Is that what you do every day in the morning as you come up?
Yes, every day.
You see, the only thing you have to think about in this problem is the direction of those two forces, isn't it? Didn't I tell you that friction is always going to oppose the motion? So that should be an easy question. There are the forces. The applied force, you see, that the tires are applying, making it go forward. Friction is always opposite, and the acceleration is in this direction, isn't it? The car is moving forward. So the net force would be equal to mass times acceleration, but in this case, the net force is caps F minus small f, which is equal to mass times acceleration. Mass is this simple algebra. 2100 take away 250 divided by 1.80, and the mass is, looking at significant figures, there are only 3 in this number, correct? That's why the final answer has 1.03 times 10 to the 3 kilograms, which is an easy question, and if I ask this on the exam and you don't do it, I'll go crazy. Okay. A 1100 kilogram car pulls a boat on a trailer. What total force? Ooh, so we're asked to find the force.
What's the force resisting?
What total force resists the motion of the car, right? So we need to find the resisting force of the car, boat, and trailer. So we got to calculate the total resisting force on all 3 of them. If the car is exerting a force of 1900 newtons on the road and produces an acceleration of 0.550 meter per second squared, the mass of the boat plus trailer is 700 kilograms. So I think that's very clear. The car alone has a mass of 1100, the other 2 together 700. It's only the car, of course, that's applying a force, isn't it?
Yeah.
Which is 1900. But friction isn't friction acting on all of them? Yeah. So that's a real question, which you should be able to do. Net force is, in this case, the applied force minus friction, which is equal to mass of the boat plus mass of the trailer plus mass of the car times the acceleration. Now why? Because aren't you asked to find the total force acting on all of them? Come on.
Yeah.
Correct? So therefore the system of interest is all of them. Are you with me? That's why I had to add all the masses. Looking for the force in all of them. So that's the applied force, that's the total friction force. Total mass of all of them and acceleration. So when you make friction the subject, you are going to get this. You have to be careful on that part, please. Everything is given, just substitute 1900 minus, got to add all the masses together, and I think you get 1800, don't you? When you add them? Yeah, because 1100 plus 700 is 1800, so we got the total mass times acceleration, force of friction is 910 newtons. Okay, let me see the hands of those who understood this. Andrew didn't understand this. Ah, you got it. Okay.
I was just on question. Is the capital F force?
Yes, that's the applied force always. Small f is friction. In all our problems, the little f is friction, right? Because I think your textbook is using the same. Go ahead.
But at first I thought I was supposed to add the net force.
No. See, the net force is sigma f. But remember, friction is always against the applied force. That's net force, that's the applied force. Right? Friction is always against. That's why you subtract. In the B part, what are you asked to find in the B part? What's the force in the hitch between the car and the trailer if 80% of the resisting forces are experienced by the boat and trailer? Got to listen to me now carefully. Now, what's the system of interest? Are all three of them?
No, just the boat and trailer.
Because you're asked to find the force in the hitch between the car and the trailer. But there is an additional thing there. 80% of the resisting forces are experienced by these two. Okay, so what's 80% of 910? Find that out first for me. Is it 910 the total resisting force, right? So what is 80% of that? How do you find that? How do you find that, Christopher? You just go 910 times 80 divided by 100. Are you with me? That is going to be the 80%. All right. So this time, you see that I've only taken the mass of the boat and the trailer. And of course, you know why, right? It's only the mass of the boat and the trailer. The acceleration is the same. Calling it F prime, so you're not confused. And you see, I put it as 0.8 F, which is 80% of friction, right? Yeah, that is the difference there. And so F prime is 700 times this plus 0.8 times the friction. Oh, yeah, this one continues, but on that computer. So you get it as 1110 newtons. 1110 Newton. That is the answer. Here it goes. A nurse pushes a cart by exerting a force on the handle at a downward angle 35 degrees below the horizontal. Take a look at this diagram. Don't you think that this is the force? Because you can see it's below the horizontal, which is going to come up, and this angle should be 35 degrees. The loaded cart has a mass of 28 kilograms and the force of friction is 60 newtons. Draw a free body diagram for the system of interest. May I ask you, what's the system of interest here? Is it the nurse or the cart? Okay, thank you. So I've shown all the forces on the cart. Now, one is the force that the nurse is applying on the cart. What's that? What's that?
Friction.
Friction. And what's that?
Weight.
The weight. Okay. B, that's it. A part finished. B part says, what force must the nurse exert to move at a constant velocity? Ooh, that word's back again. Constant velocity. So what's the acceleration? 0. Okay. Write that somewhere. Constant velocity. So all right. Now we have to resolve it into two components. Sorry. Because isn't that force acting at an angle? You got to break it up into two components. Net force along the x is 0 because acceleration is 0. Okay, here I'm resolving it. Watch it. That's F cos 35, and that is, why didn't I write it there? You know, what I'm trying to say is that this angle, rather this angle, is going to be 35, isn't it? That's why that is the adjacent side, and so it becomes F cos 35. So you're only looking at the forces along the x-axis. You see this? This is along the x-axis. This is opposite. Do we have to consider this? Come on now, do we have to consider this force? No, because it's along the y. So there are only two forces along the x. This should be bigger than this, isn't it? Because the cart is moving to the right. And why did I get 0 here? Why did I get 0 again? Because there is no acceleration. Mass times acceleration became 0. Therefore, that's an easy question. When I switch over to the other side, you know that small f will come to the right side, become positive f, isn't it? Isn't friction given as 60? Is it given?
Yeah.
Yes, that's why 60 divided by cos 35. Check it out on your calculator. You get 73 newtons as the answer to that one. Okay, who's going to read this question for me, please?
A 76-kilogram person is being pulled away from a burning building as shown in figure dot. Calculate the tension in the two ropes if the person is momentarily motionless. Include a free body diagram in your solution.
Thank you. All right, I'm drawing the diagram again, and the focus must be on understanding. So pay attention. That force is, what's that? Is that T1 or T2 that has come up now? Okay. You see all the three forces, and you also see the x component of T2. That's the y component of T2. You have T1. Where is the x of T1? What do you have to find? Calculate the tension in the two ropes, right? Looks like it didn't come up. Okay, let's see. The two components of T1 has not shown up. I do not know. Maybe I'm drawing it later on. Let's see. I'll run this whole thing through and check. No, it is not. Okay, what I had to do was I had to resolve T1 also along its two components, isn't it? Watch. Wouldn't I have one along this, which would be the x of T1, and then I would have the y of T1, correct? I'm going to complete the diagram, but imagine it exists there and try to understand this and do not copy. It's a waste of time. So, looking at this diagram, this, what I've written here, which component am I considering, x or y? Just tell me that. Now, before you do that, is this point moving?
No.
Is this point moving?
No,
Why?
because it says she's momentarily.
Thank you. It's motionless. So, if this point is not moving, what do you think the net force along the x-axis must be? What do you think the net force along the y-axis must be? 0. It's not moving at all, neither along the x nor the y. Are you with me on that? Therefore, I know that this component, which is T2 cos 10, should be equal to this component, which is T1 sine 15. All right? That's why you have T1 sine 15, which I'm going to draw in a minute, T1 sine 15, equal to T2 cos 10. Did you get that? And then the rest is math. So I take the values of sine 15, cos 10, and then bring it over to the other side and make T2 the subject. Hold on. Now let's look at the y component. Somebody tell me, what is this component? How much? T2. Hello?
76.
If this was T2 cos 10, wasn't it? So what is this? T2 sine 10. And then remember that T1 will also have a component here, which will be T1 cos 15. So when I look at the forces along the y, I have two components here, one here. So what I do is I add up both of them. Watch it. You see this? T1 cos 15 plus, are you with me on this? Add that, that should be equal to the weight. Of course, what's acting down is the weight, isn't it? 76 times 9.8, and from there I get both T1 and T2. Okay, 1700 kilograms, and it is accelerating upward from rest at a rate of 1.20 meter per second squared. That's the acceleration for 1.50 seconds. Calculate the tension in the cable supporting the elevator. Okay, going up. We did talk about this, didn't we? Do you know if the tension will become greater or smaller than the weight, please? Greater. So now you know what to do. All you got to do is m times g plus a, isn't it? That's it. It's not. So the a part, these are the forces, tension and the weight. That's all. Net force is equal to mass times acceleration, but in this case the net force is T minus mg. So T is mg plus ma, which is mg plus a. Mass is 1700, g is 9.8, plus the acceleration is 1.20. And when you do that, you get 1.87 times 10 to the 4 newtons. In the B part, it says the elevator continues upward at constant, what's that word?
Velocity.
If it's moving at constant velocity, what's its acceleration? Zero. So what's the tension? You know, if the acceleration is zero, the tension is just mg, right? Yeah. Okay. How does it? So 1.67 times 10 to the 4 newtons. And in the C part, it's decelerating at a rate of 0.6. Oh, is it still going up? What do you think? Is it still going up? Yes, but it is decelerating. Okay, so now the difference, A is 0.600 meter per second squared. But it's down, so that's what the arrow shows. Therefore, T is mg minus a. So remember that it's not only when it's going down that you do mg minus a. Even if it's going up but decelerating, you go g minus a. Is that clear? Okay. So keep all those cases in your mind. That was bad. I hit it so. Got to take it back now all the way. There's no other way. Sorry. And all. D part. What do you have to do in the D part?
Find the displacement.
How high has the elevator moved above its original starting point, and what is its final velocity? Goodness. Why 3 arrows there? Somebody? Why 3 arrows? Everybody's busy writing what they don't understand. What?
3 forces?
Not 3 forces this time, because it was moving in 3 different ways. How was it moving first? Accelerating, correct? And then it was moving at a constant velocity, and then it was decelerating. You see, that's what it shows. And in each one, we got to find the displacement, don't we? Okay, and then add them up, you will get how much it has moved. That's what I'm going to do. Velocities, displacements, I'm showing all there. That the times were different, remember the times? Y1. That is using our king, but what happened to the first term, somebody? The king is y is equal to v1t plus 1/2 at squared. But what is v1? The initial velocity? 0. Yeah, because it said it starts from rest. That's why you don't have that. But the acceleration was given, the time was given. We just calculate. So we get that, 1.35 meter. In the second case, wasn't it moving with a constant velocity?
Yes.
Okay. And you see what I'm doing is I'm doing 2 things together. I'm also finding the velocity at the end of the first type of motion, you see. Velocity, final velocity is a times t, so I'm getting its velocity. And once I have the velocity, all I got to do is multiply that velocity with the time to get y2. What is the time? In the second case, how much time was it moving? Do you see 8.50 seconds? So I got the velocity, and then I multiplied with 8.50 to give me the second displacement. And the third, okay, let me try something. This is not working because it's, all right, so in the last part it can be on top. So y3 is, how do I get all that? I'm going to stop it right there. Somebody tell me. At the end of this motion, isn't it already having this velocity?
Yes.
Come on. And then from there it's slowing down, isn't it? Yeah. So that's the initial velocity. You see, v1t. T is 3 seconds. Minus 1/2. Isn't this the deceleration given there? Yeah, that's the deceleration. Why minus? Because it is deceleration. All right. So put that 2.70 meters. So now I got to add all the three to get the total displacement. 1.35 plus 15.3 plus 2.70. Total displacement 19.35 meter. Significant figures 19.4. And what is its final velocity? 0, of course, because if people have to get out, it has to stop right at that floor. Otherwise, they'll fall. Thank you so much. I hope you understand all these problems. Now they're worked out. Good luck on the exam.